Introduction to quadratic functions. So as part of your study of functions, we worked with the function x squared before. The square function, in this section, we will study functions that result from transformations of the square function to determine their properties. So basically, if you take x squared and shift it left, right, up, down, make it wider, make it narrower, flip it, so you get a downward opening parabola instead of upward opening. These are all just transformations of x squared, and we get quadratic functions from that. All right, so what are quadratic functions? Quadratic functions are the graphs of quadratic functions, I can say, look like these. Most of these are upward openings, so we have these little U-shaped graphs. We call these parabolas, okay? If the parabola opens upward, it has a bottommost point. We call that bottommost point the vertex. Opens downward, we have a topmost point that's still the vertex. And then depending on if we take the graph of x squared, if we add or subtract a number to the x, that shifts our graph left or right. So if you see here, we have x minus 1 squared, that shifts right 1 unit. Where's another one? Oh, x minus 1 plus 2. This is the graph of x squared shifted right 1 unit, but that plus 2 shifts it up 2 units. So if you add or subtract a number from the entire function, that shifts up or down. If you add or subtract a number from the x itself, that shifts left and right. And and also if you multiply the x squared term by a constant, that makes your graph either narrower or wider. If you multiply by a constant bigger than 1, like 3x squared, you get a narrower parabola. And if you multiply by a constant like 1/2, something less than 1, you would get a wider parabola. Okay, but all of these functions are examples of quadratic functions. We're going to talk about the standard form of a quadratic function next, which most of you may be familiar with. A quadratic function is of the form f of x equals ax squared plus bx plus c. Ax squared plus bx plus c. So it's a polynomial where x squared is the highest power of x. Okay, these a, b's, and c's, they are real numbers, and a can't be equal to 0, because if a was equal to 0, then we wouldn't have a x squared term, and it would no longer be quadratic. So a polynomial where x squared is your highest power of x, that is a quadratic function. As with all polynomials, the domain of a quadratic function is all real numbers. That means you can plug in any number for x. The range, we'll talk about a little later. It will depend on whether or not you have an upward opening parabola or a downward opening parabola, but the range does have restrictions. We'll talk about how to find that. I think an example 4 today, okay? The first thing we're going to practice, though, is taking quadratic functions of the form ax squared plus bx plus c and evaluating them. This part should be easy. We evaluate functions the same way every time. You take the value of x that you're given and replace the x values in the problem with that number. So for the first one, f of x equals x squared minus 9x. When x equals 3, 0, and 2, we get f of negative 3 is negative 3 squared minus 9 times negative 3. That's 9 plus 27, which is 36, okay? F of 0 is 0 squared minus 9 times 0, which is 0. And f of 2 is 2 squared minus 9 times 2. 4 minus 18 is negative 14. All right, so remember, these tell us points on the graph of the function. On f, we have the point negative 336. We also have the point 0, 0, and 2, negative 14. All right, I'm only going to do one more of these because I feel like you guys are probably comfortable with plugging in a number and simplifying. The only thing I want you to be careful with is when you're plugging in a negative, make sure you put it in parentheses like I did there with the negative 3. I'll do g of x2 and then we'll stop. For g of negative 3, this is negative x squared minus 8x minus 10. So that's negative 3 squared minus 8 times negative 3 minus 10. That will give us negative 9 plus 24 minus 10. Negative 9 plus 24 would be 15. And 15 minus 10 is 5. So we have the points negative 3, 5. G of 0. Remember, if you plug in 0 for x in a function, this tells you where your y-intercept is, okay? So the first one we looked at, and we'll talk about this more in the next section. First one we looked at, f had a y-intercept at 0, 0. And now G is going to have a y-intercept at negative 0 squared. That's just 0 times 8 times 0, which is 0 minus 10. So those first two terms are 0, and then we get negative 10. The y-intercept here is 0, negative 10. And then the last one that we'll do here, G of 2, that's negative 2 squared minus 8 times 2 minus 10. Then that gives us negative 4 minus 16 minus 10. So what's that? Negative 30? Yeah, negative 20 minus 10, negative 30. So 2 comma negative 30 is the point on the graph. Let's get into more interesting things. I just talked a little bit about how we can find the y-intercept of a parabola. The way you find the y-intercept of any function is any point on the y-axis has an x-coordinate of 0. So plug in 0 and then solve. But for a quadratic function, the quadratic function is of the form f of x equals ax squared. That is not written right. Ax squared plus bx plus c. If we let, for any quadratic function, x equals 0, we get a times 0 squared plus b times 0 plus c. This term goes away, this term goes away, and you're just equals c. So for a parabola, the y-intercept is always going to be given by the value of c, the constant term, okay? Another important thing that we need to know about our parabola is whether it opens upward or downward. Okay, if you look at the two graphs we have here, the one on the left is an upward opening parabola. We get an upward opening parabola whenever our squared term is positive. So if a is a positive number, our parabola opens upward. And then if you have a negative x squared term, so if a is a negative number, you get a downward opening parabola like we have on the left. So upward opening parabolas have like a lowest point and then they keep going up on both sides. Downward opening parabola have a highest point and then they go down on both sides. And again, we can figure out whether our parabola opens upward or downward and what the y-intercept is just by looking at the function and determining a and c. Okay, this is summarized here for both things. Okay, so first the orientation. When a is positive, the parabola opens upward, and when a is negative, the parabola opens downward. Okay, and then for C, the y-intercept is always given by the constant term 0 comma c. All right, so in exercise 2, we're going to put those two easy things to use. Determine a and c, and then use that to find the y-intercept and determine whether or not the parabola is here, open upward or downward. For part A, f of x equals x squared minus 9x. There is no constant term here. That means the constant term is 0. So c is equal to 0, and a is equal to 1, because we have 1x squared. That means that the y-intercept is 0 comma 0, and this parabola opens upward. Okay, for part B, we have negative x squared minus 8x minus 10. That negative in front of the x squared tells us a is equal to negative 1. Our c value here is negative 10. So that means that the y-intercept is 0 comma negative 10. And since a is negative, our parabola opens downward. And last one, m of x equals negative x squared plus 5. Here a is 1 again, and negative 1 again, I'm sorry. And our constant term is 5, so c is 5. Then the y-intercept is 0 comma 5, and we have a downward opening parabola. All right, so our goal in this chapter is good, or in this section, I'm sorry, I should say, it's going to be to put information like the, if our parabola opens upward or downward, finding the y-intercept. Later, we'll talk about how to find the x-intercept, how to find the vertex, put all of this information together to sketch the graph of the parabola. These are the two easiest part, upward and downward, and then find C that gives you the y-intercept. All right, let's move on to the next important characteristic, the vertex and the axis of symmetry. First, I want to talk a little bit about what the axis of symmetry is. Every parabola is symmetric with respect to some line. What does that mean? There is some line that we can draw that will split the parabola exactly in half. And then everything to the left and to the right of that line is like a mirror image, okay? That's a line of symmetry, okay? I zoom out a little bit here. The red line that you see drawn through these parabolas are the lines of symmetry. Notice two things about this. One, it's a vertical line. We learned that vertical lines are of the form x equals some number. And then two, there's this point at the bottom of this parabola and the top of this one, the vertex, that the axis of symmetry goes through. So we have a vertical line that goes through this point of the vertex. That means the vertex and the axis of symmetry have to have something in common. They do. The equation of your axis of symmetry, forgive me, is given by the x coordinate of the vertex. And then there's an easy way to find that using what we know about A and B from our function. All right, so what things are on here that we need to highlight? We said the lowest point of an upward opening parabola or the highest point of a downward opening parabola is called the vertex. That's going to be a very crucial point that we want to be able to find. And then we said the line that goes through the vertex and splits the parabola in half is called the axis of symmetry. And we want to be able to find both of those. All right, here's a nice formula. This is an important one. Write this down. Where should we start? Okay, the axis of symmetry. The axis of symmetry is a line, and it's a vertical line, so it's going to be written as x equals some number. What is the number? We can figure out what x equals for the axis of symmetry by using negative b over 2a. Remember, a and b are the coefficients given to you in the function. You take negative b and divide by 2a, that gives, or x equals that gives you the axis of symmetry. And then what else does this give you? This also tells us the x coordinate of the vertex. The vertex is a point. So it's going to have an x coordinate and a y coordinate. But once you find that axis of symmetry, that also tells you what the x coordinate of the vertex is. And then how do we find the y coordinate? Take whatever you get for x, plug it back into the function, and we get the y coordinate, f of negative b over 2a. So the vertex is going to be a point that will look like this. Whatever negative b over 2a is, that's your x coordinate, and then plug that back into your function to get your y coordinate. Negative b over 2a comma f of negative b over 2a. So being able to find this negative b over 2a is very important because it gives us two big things. Helps us with our axis of symmetry, and it gives us the x coordinate of our vertex. All right, let's use that in our next example. So in practice problem 3, it says use the equation of the quadratic function to determine the axis of symmetry and the vertex of the parabola. Again, we're going to be using x equals negative b over 2a. So for part A, if you need practice with this in the beginning, you can start off by identifying your A, B, and C. You don't really need C, but you can identify it. For this function, A is equal to 1, B is equal to negative 9, C equals 0. For the axis of symmetry, we want x equals negative b over 2a. That would be x equals negative negative 9 over 2 times 1. And then just simplify it. That would be 9 over 2. Usually we just leave it as a fraction in simplified form. If your fraction converts to a decimal that terminates, you can write it as a decimal. That would be 4.5. Or you can just, like I said, leave it as 9 over 2. That's perfectly acceptable. And in most cases, it's better to leave it as a fraction. Okay, one thing I want to be clear about. The axis of symmetry is not 4.5. The axis of symmetry is a line. So the axis of symmetry is x equals 4.5 or x equals 9 over 2. You can write it either way. You have to write the x equals part because that is how we know that we're writing an equation of a line and not just a number. Now, the nice part about this is, remember, negative b over 2a gives us two things. So yes, this is our axis of symmetry, but this also tells us the x coordinate of the vertex. So for our vertex, we already did some of the work. X is going to be equal to 9 over 2. Yeah, I believe that. And then for y is going to be equal to f of 9 over 2. What does this mean? We're going to take that x coordinate, plug it back into the original function, and then find y. All right, so x is equal to, that'll be 9 over 2 squared minus 9 times 9 over 2. 81 over 4. Sorry, I was thinking in my head. Minus 81 over 2. Writing these with the same denominator, this will give us 81 over 4 minus 162 over 4. And then finally, when we subtract, that'll give us a negative 81 over 4. Just going to erase a little bit down here and give us some more space. All right, last thing, I just want to write my vertex as an ordered pair. We said x was equal to 9 over 2, and then we just calculated y to be, let me just double check it, make sure I believe me. Yeah, y is equal to negative 81 over 4. So the vertex is the point 9 over 2, comma, negative 81 over 4. Fun stuff. So you compute negative b over 2a, x equals that number is your vertex, is your axis of symmetry. That also tells us what x equals for the vertex, and then you plug that number into the function to find y. All right, then in part B, we have g of x is negative x squared minus 8x minus 10. So a is negative 1, b is negative 8, c is negative 10. We don't really need c again, but should be able to identify it. All right, for the axis of symmetry, we have x is equal to, again, negative b over 2a. I'm just going to keep writing it for the first few times just so you remember it. That would be negative 8 over 2 times 1, or negative 1. Lots of negatives going on here. So we'll get 8 over negative 2, which is negative 4. So our axis of symmetry is x equals negative 4. Then for our vertex, we know that x equals 4 or negative 4. Y is going to be equal to g of negative 4. That's negative 4 squared minus 8 times negative 4 minus 10. All right, that's negative 16. Yeah, Negative 4 squared is 16, and then they have a negative in front, so negative 16 plus 32 minus 10. That would give us 16 minus 10, which is 6. Putting those two things together, our vertex is at negative 4, 6. All right, and then last part, our function is negative x squared plus 5. For negative x squared plus 5, the a value is negative 1. The b value is 0. Notice how there is no x term here. So b is 0. And the c term is 5. We don't really need c again. We need a and b though. For the axis of symmetry, we have x is equal to negative b over 2a, which is negative 0 over 2 times negative 1. No such thing as negative 0, but the point is this whole thing is 0. So the axis of symmetry is a line, x equals 0. That's the y-axis. And then the vertex, that's going to be given by x equals 0, and y is equal to f of 0, which is negative 0 squared plus 5, or 5. This is the easiest one. So we get 0, 5 for our vertex. All right, we're building up to being able to sketch out these entire parabolas, but I just want to show you really quickly on Desmos what this looks like, where your vertex is, what this means. So let's start with problem A. If we just look at the function x squared minus 9x, automatically we should be able to look at that and say, okay, that's an upward opening parabola. Let's just look on Desmos really quickly. What was the graph? X squared minus 9x. All right, zoom out a little bit so we can see. Boom. Here is the graph of the parabola. It's upward opening like we anticipated. I'm going to also graph the line y equals 9 over 2. So you can see that the blue line, which is the axis of symmetry, divides that parabola exactly in half. That's what the axis of symmetry is supposed to do. So we got the right one. And then if we look at just the parabola again, this bottommost point is the vertex, and that's given by 9 over 2, which is 4.5, comma negative 81 over 4, that is negative 20.25, if you put it in decimal form. We said earlier that the domain of a quadratic function is all real numbers. You can plug in anything for x, but for the y values, we end up having this either bottommost point or a topmost point, depending on whether or not your parabola opens upward or downward. So there is going to be a restriction on the y values, or on the range. To help you figure out what your range should be, you need to determine if your parabola opens upward or downward, and if your vertex is a maximum or minimum. If the parabola opens upward, your vertex is a minimum. So let's say this point is, okay, I'll call it C comma D, because that's all I can think of right now. Okay, let's say the vertex is the point C comma D. Then for the range, we are considering the y values. So that means whatever this value D is, that's the y coordinate, that's the smallest possible value we can have for y. So the range would be any number from D, and then the parabola is going upward. So to go from D to infinity, and D would be included. Okay, if we had a downward opening parabola, and if our vertex is up here at the point C comma D again, in this case, D is the upward or the highest point. It's the largest value that the outputs can be. All of the other y values would be less than D, and then your range would be negative infinity up to D, and the D is included. So using what we had in the last section for our vertices, we can use the vertex to help us figure out what we have here. For part A, we can say from exercise 3, we get that the vertex was at 9/2, comma, negative 81/4. So this means that and this was an upward opening parabola. We should be able to determine both of those things. So that means that negative 81/4 is a minimum. It's the smallest possible value that we can get for our output. So our range in this case is going to be from negative 81/4. If you prefer to write this as a decimal, that's fine, to infinity. What does this mean? For any x value that you plug into this function, the outputs or the y values have to be between negative 81/4 and infinity. Can't be anything less than negative 81/4. All right, for part B, hold on, I have to scroll back up really quickly. This one was negative 4,6 for the vertex. So vertex is negative 4,6. This time we have a downward opening parabola. That means that the vertex is a maximum. So I can write that here. Vertex is a max. That means the y coordinate of the vertex is the largest possible value we can get for the outputs. So that means that the range is going to go from negative infinity to 6. And the 6 is included. That's our range. And for the last one, this problem's different. I don't know why they changed it, if it was on purpose. The last problem we had m of x is equal to negative x squared plus 5. This one's negative x squared plus 9. So that's going to change where our vertex is. So let's just calculate it. For the vertex, we would have x equals negative b over 2a. Again, that's 0 over 2 times negative 1, which is 0. So x equals 0, and y is equal to negative 0 squared minus or plus 9, which is 9. So our vertex is at 0, 9. All right, now that we know that, if the vertex is at 0, 9, this is a downward opening parabola. The vertex is a maximum. So our range is going to be from negative infinity all the way up to 9. Positive 9. All right, and that's it. So again, to determine the range, that's what's all of the possible outputs you can get. You want to use your vertex, use the y coordinate. If the parabola opens upward, the y coordinate is the smallest output. If the parabola opens downward, the y coordinate gives us the largest possible output. All right, look at us rolling. We only have 2 more things to do. And the next thing is kind of easy because we've done it a gajillion times, I would say. We need to find the x-intercepts. You might be saying, I haven't found the x-intercepts of a quadratic function before. But remember, the x-intercepts are going to occur whenever your quadratic function is equal to 0. The output is equal to 0. When y equals 0, we're on the x-axis. So that gives us our x-intercepts. So if we take these quadratic equations and set them equal to 0, then ta-da, we get our x-intercepts. Where have we done this before? Quadratic functions are polynomials. We had a whole chapter of solving polynomial equations. We usually do it by factoring. So we're going to talk about how to solve these by factoring. So in problem 6, we're going to do everything. We're going to identify whether or not the parabola opens upward or downward, find the y-intercept by looking at the value of c, find the x-intercepts by setting the function equal to 0 and trying to factor and solve. And then we're going to find the vertex and axis of symmetry, put all of that information together, and then sketch out a graph of what the parabola might look like. Okay. Is there an exact order that you have to do this in? No, there's no particular order that you have to do it in. I usually do intercepts first and then the vertex and axis of symmetry, or axis of symmetry and then vertex. You could do the axis of symmetry first and then the vertex and then the intercepts. Doesn't really matter. I think in the book there is a specific order that they go in. And this is just to help you keep track of things. So start off by determining if it opens up or down, then find the axis of symmetry, find the vertex, find the y-intercept, which should be super easy, find the x-intercepts, okay? I'm gonna start with the intercepts though, because that's where we have not practiced. For problem 1, hope we have enough space for all of this stuff. X squared minus 16, this parabola opens upward. And if it's helpful for you, draw a little picture so that tells us the vertex is going to be at the bottom. Okay. If we wanted to find the intercepts, the y-intercept, that's an easy one, is given by 0, c. C in this case is negative 16. So the y-intercept would be 0, negative 16. All right. For the x-intercepts, this is where we have a little bit of work to do. So we would have x squared minus 16 equals 0. X squared minus 16 is a difference of squares, so that factors to x plus 4 times x minus 4 equals 0. Setting each factor to 0 gives us x equals negative 4 and x equals positive 4. We want to write our intercepts as ordered pairs. So the ordered pairs would be negative 4, 0 and 4, 0. Let's highlight this stuff. So y-intercept, x-intercepts. Again, you'll just be solving the quadratic equation, which is we can do by factoring. All of these we should be able to do by factoring. Some of them are not factorable, but we'll talk about that at a different time. We'll use the quadratic formula there. All right, do I have enough space? We'll see. Next part, we need to find the axis of symmetry. The axis of symmetry in this case, notice here B is equal to 0. Anytime B is equal to 0, your axis of symmetry is just 0. But let's show all of the steps. I'm going to abbreviate this just axis of sim. Okay, we'd have x equals negative b over 2a. That's negative 0 over 2 times 1, which is 0. So x equals 0 is the axis of symmetry. Then using this for our vertex, we know x equals 0. That's already given to us. We just did it. And y would be equal to f of 0, which is 0 squared minus 16, or negative 16. We've seen this part before. So if we put this together, we get 0, negative 16 as our vertex. I think we have all of this stuff now. And why I said we've seen this before is, notice the y-intercept and the vertex are the same here. So this is a case where your vertex is on the x-axis. Okay. Let's put all of this stuff together and try to sketch. All right, when you're trying to sketch a quadratic function, you want to start off by trying to see how much space I need down here. You want to start off by plotting your x-intercepts, y-intercept, and vertex, and then use whether or not your parabola opens upward or downward to connect the dots and sketch your parabola. All right, I'm going to try to draw the scale here as neatly as possible. 1, 2, 3, 4. 1, 2, 3, 4, negative 4. I'm not going to draw 16 negative tick marks, so we're going to count by 4s on the y-axis. So that's 4, 8, 12, 16. Negative 4, negative 8, negative 12, negative 16. All right, if we plot our points that we have here, I'll do it in red. Negative 4 is 0, and positive 4 is 0 are x-intercepts. 0, negative 16 is our y-intercept. And we know that our parabola is going to open upward. So we'll draw as neatly as we can the shape of a parabola that goes through these points and opens upward. And just draw arrows at the end to indicate that the parabola is going to continue opening up. And that's it. Ta-da, 1 down, 2 more to go. Any questions about part A? All right, then on to part B. We're going to do these same things. All right, so we need to know whether or not the parabola opens upward or downward, the x-intercept, the y-intercept, the axis of symmetry, and the vertex. First thing, f of x equals x squared minus 3x. This parabola opens upward. Okay, so again here, our vertex is going to be a minimum. Next thing, for the y-intercept, notice here the value of c is 0. X squared minus 3x, a is equal to 1, b is equal to -3, c equals 0. So the y-intercept would be at 0, 0. All right, not much to do there. For the x-intercepts, we have to factor. If we take x squared minus 3x and set it equal to 0, that gives us x times x minus 3 is 0. X equals 0, x minus 3 equals 0, so x equals 3. We have 2 x-intercepts here. One at 0, 0, and the other at 3, 0. Y-intercept is 0, 0, which is of course also an x-intercept. And then 3, 0 is also an x-intercept. All right, then axis of symmetry. That would be x equals -b over 2a. So x equals -3 over 2 times 1. That's 3 over 2, or if you want to write it as 1.5, you can write it as 1.5 as well. 3 over 2, or x equals 3 over 2, I'm sorry, as our axis of symmetry. And then for the vertex, we use the axis of symmetry, x equals 3/2, and y is going to be equal to f of 3/2. So that's 3 over 2 squared minus 3 times 3 over 2. All right, let's simplify this. Yes, there are fractions, but that's okay. We can deal with them. That's 9 over 4 minus 9 over 2, which would be 9 over 4 minus 18 over 2. And finally, that's -9. Oh, I'm sorry, 18 over 4. And finally, that's -9 over 4. So our vertex is the ordered pair 3 over 2, comma, -9 over 4. All right. Now let's put all of this stuff together. Don't have much room to sketch. I'm going to have to just come over to the side a little bit. All right, so we want to draw our axes. Be very neat. I didn't label my axes last time, which is very bad. You should label your axis, your x and y axis. -9 over 4. Okay. Label your x and y axis and draw your scale. What information do we have here for the scale? Or what points do we need to plot? We have to plot 0, 0. We have to plot 0, or 3, 0. And then we have to plot 3 over 2, which is about 1.5, comma, -9 over 4. -9 over 4 is, what's that, 2.25? -2.25. Okay. So let's go 1, 2, 3, 4. 1, 2, 3, 4. I want my y-axis to go down a little bit more, just so I can get 1 and 2 in here. So -1, -2. And then let's plot these points. We'll make this one green. 0, 0 is here. Then we had 3, 0. And then we had 1.5, which is right in the middle here, comma, negative 2.25. That would be about here. And then we want to draw a parabola that goes through these. Try to draw even on both sides. Mine was not even on both sides, but we can fix it. Maybe we can't. All right. Sorry, my wrist just keeps hitting everything today and ruining our picture. All right, there we go. Also, I did not draw this on the last graph. I should draw this on both graphs. We usually do also sketch the axis of symmetry, and we use a dashed line to show where the axis of symmetry is. So the axis of symmetry in this case would be x equals 1.5, which is right here. Your axis of symmetry should go straight through your vertex. And for this one, it was just the y-axis. We can label these things too. X equals 3/2. And if there are any points that aren't clear, you should label those as well. So for the vertex, we can label 3/2, comma, -9/4. All right, one more of these, and then we're done with this part. Part C, we have f of x equals 2x squared minus 6x minus 20. This is an upward opening parabola again. Oh, they all open upward. That's no fun. But yeah, it's an upward opening parabola. The y-intercept is given by C. Oh, let me put it up here. A equals 2, B equals -6, C equals -20. So the y-intercept is 0, comma, -20. Since I have a little bit of space to the right, I'm going to write the x-intercept this way. The x-intercept would be 2x squared minus 6x minus 20 equals 0. We have to solve this. We can factor out a 2. So remember, I feel like I told you guys back in chapter 5 that factoring never goes away. Here we go again. We need factoring. This is 2 times x squared minus 3x minus 10, which would be 2 times x minus 5, x plus 2. All right, if we set those factors equal to 0, 2 can't be equal to 0. So we get x minus 5 equals 0, x plus 2 equals 0, x equals 5, and x equals -2. So our intercepts are 5, 0, and -2, 0. Right, so 0, -20, and then 5, 0, and -2, 0, not 2, 0. All right, what's left? I want to make sure we have room at the bottom there to sketch as well. So let me kind of draw my little cutoffs here. Boom. For the, what's next? Axis of symmetry. We would have x equals -b/2a. That's -6 over 2 times 2. So we get x is equal to 6/4, or 3/2. All right, so that's the axis of symmetry, x equals 3/2. And then last part, the vertex. We know x is equal to 3/2. Y is going to be equal to f of 3/2, which equals 2 times 3/2 squared minus 6 times 3/2 minus 20. Ah, yes, we get to simplify this. Fun stuff. So we have 2 times 9/4 minus 6 times 3/2 would be 18/2 minus 20. All right, if I simplify things a little bit, it works out not too bad. This would be the 2 and the 4 cancel out, so that would be 9 over 2. 18 over 4, which simplifies to 9 over 2. 9 over 2 minus 18 over 2 minus 20 would be, or negative 20 would be negative 40 over 2. All right, 9 minus 18 minus 40 would give me negative 9 minus 40, or negative 49 over 2. So putting that together, our vertex is 3 over 2, comma, negative 49 over 2. A little bit less than negative 20, or a little bit more than negative 25. Okay, I'm putting all of this information together to sketch. So we need to go negative 2 to 5 for the x's, and then we need to go all the way down to like a negative 25 for the y. All right. One, two, three, 4, 5. 1, 2, 3. So that's negative 3, negative 2, negative 1. 1, 2, 3, 4, 5. For the y's, we're going to be counting by 5s. 5, 10, 15, 20, 25. So that's negative 25 down here. Okay, and then if we plot our points, what color did we use? Pink. Let's use pink. All right, so the x-intercepts, I can see those right there. They're 5, 0, and 0, or negative 2, 0. The y-intercept was 0, negative 20, which would be here. And then at 1.5, comma, negative 49 over 2. So that's negative 24.5. We have our vertex. That is about here. Maybe over just a pinch. There we go. That should be pretty good. All right, we want to draw an upward opening parabola that goes through these points. The left side should look like, or right side should look like this. And then the left side should look like this. And then success. That's our nice hand-drawn parabola. And lastly, if I wanted to just draw my axis of symmetry, 1/2 is about there. So this is x equals 3/2. And then remember to label your other points. This is 3/2, comma, negative 49 over 2. And then the other points on the axes are pretty clear. But if they're not, you should label them. Look at us, we've done so much today. All right, now we know how to graph quadratic functions. The last little thing in this section, everybody's favorite, word problems and applications. So we're gonna go through a couple of application problems where quadratic functions are used. I'll just jump straight to the exercises here. One common one that you see is if you have an object that's falling that can be modeled with a quadratic function, or something being thrown in the air and you want to know the height, or like a baseball is hit and you want to know the height or travel the path. Those are all things that can be modeled with quadratic functions. Here, for part 1, it says a stone is thrown upward vertically, upward from a height of 20 feet at a rate of 160 feet per second. Use the quadratic function h of t equals negative 16t squared plus 160t plus 20 to find how long it will take the stone to reach its maximum height. And what is the maximum height? Aha, maximum height. And we want to know how long it would take the stone to reach its maximum height. And what is the maximum height? If this function is, or if this situation is being modeled with a quadratic function, when we hear the terms maximums and minimums, we should know that, oh, those usually occur at the vertex. So for this function, does it have a maximum? It's a downward opening parabola because our a value is negative 16. So yes, this is a downward opening parabola and the maximum occurs at the vertex. Okay, but the vertex is a point. We're asked for a time and a height. So how can we take the coordinates of that point to figure out the time and the height? remember the inputs here, the t values are our times. So the input or the t coordinate of the vertex tells you the time, and then the outputs give us the height. So the h coordinate of the vertex will give you the height. Okay. Input gives you the time, output gives you the height. But essentially, we need to find the vertex here. So for number 1, we need space. I'll write it down at the bottom. We have h of t equals negative 16t squared plus 160t plus 20. A equals negative 16, B equals 160, T equals 20, C equals 20. To find the vertex, we need x equals negative b over 2a. That's the x coordinate. So negative 160 over 2 times negative 16. That would be 5. Yeah, because negative 160 divided by negative 16 is 10. And then 10 divided by 2 is 5. All right, so that one isn't too bad to actually calculate. So also, let me take it a step back here. I did something bad. I'm using the wrong variable. Our input variable was t here, so this wouldn't be the x coordinate. It would be the t coordinate. So t is equal to 5. All right, that gives us part of our answer. T equals 5. That's 5 seconds. All right, but we also need to know what h of 5 is. So h of 5 is negative 16 times 5 squared plus 160 times 5 plus 20. Negative 400 plus 800 plus 20, which leaves us with 420. All right, so our vertex is the point 5, 420. What does this mean? The input is the time, the output is the height. So to answer our question, we would say after 5 seconds, what are we throwing? Forgot what we were throwing in this case. The stone reaches a maximum height of 420 feet. Okay. The stone reaches a maximum height of 420 feet. Be sure to include units after 5 seconds. Number 2, a retailer who sells backpacks estimates that by selling them for X dollars, he will be able to sell X minus 100 backpacks in a month. The quadratic function R of X equals negative X squared plus 100X is used to find the revenue received when the selling price of the backpack is X. So if they're selling the backpack at X dollars and they expect to sell 100 minus X of them, when you multiply those two things together, the price times the number you sell, that gives you something called a revenue. So this is the revenue function, negative X squared plus 100X. Find the selling price that will give the maximum revenue and find the maximum revenue. So again, even though this sounds like it's a totally different situation, the work is basically the same. We have a quadratic function, R of X equals negative X squared plus 100X. We have a downward opening parabola here. The vertex tells us where the maximum occurs. And then from here, we just want to find the X coordinate of the vertex and the Y coordinate. X tells us the selling price. I just want to highlight that. The selling price is X. So X tells us the selling price. And then when we plug X into the revenue function, that tells us the revenue, how much money we make from selling it. Okay, so we're trying to find the vertex here. X would be equal to negative B over 2A. In this case, that's negative 100 over 2 times negative 1. Yeah, so that is 50. X is equal to 50. So we're selling the backpacks for $50. And then R of 50 would be negative 50 squared plus 100 times 50. Negative 50 squared is negative $2,500. And then 50 times 100 is $5,000. So we get $2,500. All right, so the vertex is at 50, 2,500. 50 tells us the selling price. And then the 2,500 tells us the revenue. All right, so we would say, the question is, find the selling price that will give the maximum revenue. A selling price of $50 gives a max revenue of $2,500. And that would be the end there. All right, so if we have situations that can be modeled with quadratic functions, in which there are a few, then if we're asked to find the maximum, or sometimes depending on the situation, if you have an upward opening parabola, you would be asked to find the minimum. Those occur at the vertex. For section 8.2, we are talking about translating graphs of quadratic functions, or transformations, I should say, of quadratic functions. In the previous section, we studied properties of functions, quadratic functions, and graphed the quadratic function in standard form. In this section, we will study transformations of the square function and learn how to graph quadratic functions by comparing their graphs with the square function. So what does this mean? Basically, every single quadratic function is just a shift of x squared. It's x squared shifted up, down, left, right, and then either expanded or condensed. So it's wider or narrower, but it's just a shift of x squared. So we're going to look at a different form of the equation, the vertex form, and talk about how from the vertex form we can identify the vertex and then graph a quadratic function. Okay. Graphing transformations of squares. Let's talk really quickly about these rules. Okay. So if you are adding, or if you have a positive number h, if you add a number to the x, that shifts your graph to the left x or h units. If you add a number to the x, and let me highlight what I'm talking about here so you can see it. Boom. Instead of x squared, we have x plus h squared. This shifts our graph to the left h units. If you subtract a number from the x, this shifts our graph to the right h units. Okay? So adding or subtracting from the x shifts left or right. An example of what this would look like. Instead of x squared, if we had x plus 3 squared, this would shift to the left 3 units. Or if we have x minus 5 squared, that would shift to the right 5 units. Okay. All right. Next, transformations, shifting up or down. These are the easiest ones. If you want to shift your graph up or down, instead of adding or subtracting a number just to the x, you add it to the entire x squared function. So if you have x squared plus k, that moves up k units, x squared minus k moves down k units. So something like x squared plus 3 is up 3 units. And x squared minus 5 is down 3 units. Then let's say we put this together. If I have some function that's f of x equals x plus 3 squared minus 5. So there's a 3 being added to the x. That tells us that we're shifting 3 units to the plus 3 would be to the left. Seems a little opposite of what you would normally think, but adding a 3 to the x shifts to the left. And then the minus 5 means you're moving 5 units down. All right. So using that information, we're going to do practice exercise 1 here. Graphing transformations of the square function. Explain how the graph of g of x is obtained from the graph of x squared. Identify the vertex and verify your answer using a graphing utility. So we want to do what I just did in my last really quick example. Look at the term that's being squared. What number is being added or subtracted from x? That tells us our horizontal shift. And then look at what number is being added or subtracted from the entire squared part. That tells us our vertical shift. And then we can put those two things together. So first, we have this -1 from the x. That tells us that we're going to shift horizontally 1 unit to the right. Okay, so we have a horizontal shift 1 unit right. And what are we shifting? It's the graph of x squared. So you start with the graph of x squared and then shift it 1 unit to the right. Okay, the -3 on the outside here tells us we're going to shift 3 units down. And if you think about the graph of x squared has its vertex at 0, 0. So when we move 1 unit to the right, that's going to move the vertex 1 unit to the right, and 3 units down, that moves the vertex 3 units down. So that 1 unit to the right changes the x coordinate of the vertex. And the 3 units down changes the y coordinate of the vertex. And if we put those two things together, the new vertex would then be at, we would move 1 right, 1, and then 3 down, -3, 1, -3. Using that same idea for part B. For part B, we have g of x is equal to x plus 1 squared plus 3. All right, the plus 1, the x being added to the 1, tells us that we want to shift 1 unit to the left. And then we're going to shift the plus 3 units up. So 1 unit left and 3 units up. That would give us a vertex at -1, 3. The other thing that we need to talk about is when our graph is wider or narrower than x squared. And that is depending on what the value of a is. There's a table here. There we go. If a is equal to 1, or the absolute value of a is equal to 1, if you have -x squared or x squared, then you're going to get a graph that is exactly the same width as x squared. Okay. If your a value is bigger than 1, then that means that graph is going to grow faster. So you're going to end up with a graph that's narrower than x squared. So if we look at, we'll look at the graphs of these. And then if you have something where a is, the absolute value of a, is less than 1 or between 0 and 1, you end up with a parabola that is wider than x squared. And last thing, if a is less than 0, we get a reflection of the graph over the x-axis. So we get a downward opening parabola, but we knew that. All right, let's go to Desmos really quickly to compare a few things. All right, we're going to look at x squared. This is our basis where we're starting from. If we have an a value that's bigger than 1, so let's look at 3x squared, we're going to end up with a narrower parabola. Notice how the purple parabola is more narrow than the green one, okay? But if we pick a value that's between 0 and 1, like 1/2 x squared, we'll end up with a wider parabola. So 1/2 x squared, as you can see, the black parabola is wider than the green one, which is x squared, and the purple one, which is 3x squared. Okay, so when we're talking about the width, wider or narrower, we're talking about compared to x squared. All right, our other big form, we talked about the standard form of a quadratic function. I'll remind you up here, standard form is f of x equals ax squared plus bx plus c. And then we also now have the new vertex form. This is another way we can write out the equation of a parabola, which quickly allows us to identify the vertex. So a quadratic function with the vertex h comma k is written in vertex form as f of x equals a times x minus h squared plus k, with a not equal to 0. Okay, a times x minus h squared plus k. And h comma k is the vertex. A is the same as what we learned before. It's the coefficient of the x squared term. All right. So if we're given something in vertex form, it should be easy for us to identify the vertex. And once we identify the vertex, we can identify the vertex. We can also identify A, determine whether or not the parabola opens upward or downward, find the axis of symmetry. Once you know the vertex, the x coordinate gives you the axis of symmetry. So we can find a lot of information. Let's just write those things out really quickly. We said our vertex is h comma k. Also, the axis of symmetry would be x equals h in this case. And then, of course, if A is positive, it opens upward. If A is negative, the parabola opens downward. All right, that gets us to exercise 2. So for exercise 2 here, we want to know whether or not these parabolas open upward or downward. What's the axis of symmetry? And what's the vertex? I'm going to write up here what the standard form is again so that you can, the vertex form is so you can compare. F of x equals a times x minus h squared plus k. We want to identify what this h is and what the k is. And also notice that in the parentheses, the h is being subtracted. Keep that in mind. So for f of x equals negative 3, x plus 5 squared minus 2. I'm going to rewrite this a little bit. This would be negative 3 times x minus negative 5 squared minus 2. Basically, if your term in parentheses has an addition, think the opposite. That means the h term is going to be negative. Sorry, h term here is negative 5. Just identifying a few things. A is negative 3. Our h value is negative 5. And k is negative 2. Remember that h comma k tells us what the vertex is. So in this case, A is negative, so we have a downward opening parabola. What else are we asked for? The axis of symmetry is x equals h. So that's going to be x equals negative 5 is the axis of symmetry. And the vertex is h comma k, so negative 5 comma 2. Just be careful with your sign there for the x term. For part B, f of x equals 5 times x minus 2 squared plus 7. So A in this case is 5. H in this case is 2. And K is 7. So this parabola opens upward. The axis of symmetry is at x equals 2, and the vertex would be at 2, 7. So it's just another way to look at a parabola's equation and be able to quickly identify your vertex. Okay, so writing the equation of a quadratic function in vertex form. If we're given the vertex and we're given A, that should be pretty easy. We just plug those things in. If we are not given the vertex and given A, we can find the vertex by using negative b over 2a. That's what's happening here in example 4. We're given the standard form, 3x squared minus 6x plus 7. We use the values of a, b, and c to find the x coordinate of the vertex and the y coordinate. So x equals 1 here. Y is equal to 4. So that gives us our h and our k. Our vertex here is at 1, 4. Once you have the vertex and you know A, you can plug those things into the standard form of the equation. I'm sorry, the vertex form of the equation to write it out. All right. And the big topic, the last big one, writing an equation of a quadratic function in vertex form by completing the square. All right. What does completing the square mean? All right. A perfect square, if you think about numbers, is a number. Let's just think about numbers for a minute. That is the square of some whole number. So like 4 is a perfect square because it's 2 squared. 9 is a perfect square. 16 is a perfect square. 25 is a perfect square. That's 5 squared. 64 is a perfect square. That's 8 squared. 100 is a perfect square. That's 10 squared. Just like we have perfect squares for numbers, we can have perfect squares for trinomials. Okay. If we have x plus b squared, that is equal to x squared plus 2bx plus b squared. That's an example of a perfect square trinomial. So we say that x plus b squared is a perfect square, and the trinomial x squared plus 2bx plus b squared is a perfect square trinomial. Okay, our goal is to take a perfect square trinomial and simplify it into a perfect square. So we're going to take something that looks like x squared plus 2bx plus b squared and write it as x plus b all squared. All right, that's what we're going to do. Every single time we do this, every time that we have a problem, it's not always going to be a perfect square trinomial. So our goal is to force it to be one. So we're going to add or subtract things on both sides of our equation to create a perfect square trinomial and then simplify it to x plus b all squared. There's an example done here for us, but I like to simplify it. Here we go. How to complete the square. So you're always going to start off with some x squared plus bx. You're going to have those two terms. To create a perfect square trinomial, we're going to add b over 2 squared to x squared plus bx. And then, of course, we can't just add something and call it equal to what we had before. We have to subtract it as well. So add and subtract that term. If we have x squared plus bx plus b over 2 squared, this simplifies to x plus b over 2 all squared. It simplifies to a perfect square like this. That's the idea that we're using. So we're going to need to be able to identify b, find b over 2 squared, whatever that number is, we'll add it to both sides, or we'll add it and subtract it from our equation, and then we'll simplify like this. If you have not done completing the square before, like I said, this might be a little tricky for you. You'll need to practice this, but we'll do a couple of examples. Jump down to the example section. All right, last example, writing the equation of a quadratic function in vertex form. So we'll practice completing the square on all of these. For problem 1, this one's easy. If a equals 5 and the vertex is -2, -7, that's h and k, then when we plug this into f of x equals a times x minus h plus k, we get f of x equals 5 times x minus -2, which would be x plus 2, and then plus -7 minus 7. Oh, I missed the square. That's the most important part. Sorry, guys. That's a times x minus h squared plus k. Part B says identify the vertex and write the vertex form of the quadratic function. For number 2, I have to write down here 2a. F of x equals x squared minus 14x plus 51. We can use what we did previously to find the vertex. So x is going to be equal to negative 14 over 2 times 1, which would be 14 divided by 2, or 7. That's the x coordinate of the vertex. For the y coordinate of the vertex, of course, we just plug this back into the function. So f of 7 equals 7 squared minus 14 times 7 plus 51 equals 2. Great. Okay. So putting these two things together, our vertex is 7, 2. This gives us h and k. Also from the original problem, we see that a is equal to 1. And then if we put those things together, f of x is equal to 1x. You don't have to write the 1. So this would be x minus 7 squared plus 2. For 3b, we have f of x equals negative 3x squared minus 6x plus 1. Remember I said we want to kind of isolate the x squared plus bx part? Well, we have a negative 3x squared here. Before we do anything, we want to kind of factor out the negative 3. So we can write this as negative 3 times x squared plus 2x. And then we still have a plus 1 over there. And why did I leave that space? I left that space because we want to complete the square. So over to the side here, we're going to have to find b, and then b over 2, and then b over 2 squared. When we're thinking about what the b is, we're just looking at what's inside of the parentheses here, because that's where we're completing the square. We have the first 2 terms. We need to figure out what the last term is. Okay, give me 1 second. Okay, I'll come back to that. So here, if we look just inside of the parentheses, b is equal to 2. Then b divided by 2 is 2 divided by 2, which is 1. And b divided by 2 squared would be 1 squared, which is 1. So this one isn't that bad. All right, remember, we always want to add b over 2 to both sides. So if we add b over 2, it's calling me. Okay, let me highlight this. Add the b over 2 squared. That's here. That's what we're going to add here. So we get x squared plus 2x plus 1. This completes the square for, well, makes a perfect square trinomial. X squared plus 2x plus 1 simplifies to x plus something squared. That 1 is being multiplied by a negative 3. So essentially we added a negative 3 to balance that out. We need to, so adding a negative 3, subtracting 3, we need to add 3 on the outside. That balances adding the 1 inside of the parentheses. Okay, now for the simplifying. And I promise we're almost done. This is the last step. Inside of the parentheses, x squared plus 2x plus 1, that simplifies to x plus 1 squared. Whatever your b over 2 is, see over here we have b over 2, that's what ends up being here every single time. And then last part, we have plus 1 plus 3 on the outside, so that ends up giving us a plus 4. And that is our vertex form. And then last thing for real. For both of these problems, we were asked to identify the vertex. Once you have it in vertex form, it should be pretty easy to identify the vertex. For part 3b, well, I have one of the parts highlighted there. We have an x plus 1 and then a plus 4 on the outside. That plus 1 tells us that h is negative 1. And then plus 4 tells us that k equals 4. So the vertex is negative 1 comma 4. And for 3a, we had x minus 4 squared minus 12. So h is 4, k is negative 12, and the vertex is 4 comma negative 12.